Yeah, so thank you very much for the invitation. It's a pleasure to be here. I'm going to be talking about Chern-Schwarz-McPherson classes and mother classes for Schubert varieties. So this is joint work with in several collaborations. One collaboration is with Paolo Alufi, Jörg Schurman, and Changjian Su, and the second collaboration is with Rahul Singh. And actually, Rahul is the last student of Lakshmi Bai. He was also my postdoc. We had several papers together. And in some sense, you will see, hopefully by the end of the talk, you will see that some of the key ideas that sit behind the calculations I'm going to show you really come from Rahul's insights. And Rahul worked with Lakshmi Bai while he was a graduate student. So yeah, so let me tell you what are Chern-Schwarz-McPherson classes and what are mother classes and how do they fit into the larger context here. So let me start with the classical Poincaré-Hopf theorem. So by the way, if you can't see my writing, just let me know. I'll try to write bigger. So Poincaré-Hopf theorem, or a version of it, says that if X is smooth and compact, then you can calculate the topological Euler characteristic, maybe with compact support, as an algebraic quantity in some sense. It's the top Chern class, of the tangent bundle of X. So this integral just means the degree of this top Chern class. So then the question is whether such a statement can be generalized to the singular case. And in the singular case, in order to make the statement, I'm going to introduce a new object, which is the group of constructible functions. So X in this case is just any algebraic variety. And then f of X is going to be just formal combinations, finite formal combinations. So Z inside X, constructible. And I want this sum to be finite. So this is going to be just some multiplicities, integer multiplicities times this indicator functions of Z. So mz here is an integer. So this is called the group of constructible functions. It's obviously a group, the group of constructible functions. It has some functoriality properties. So if you have a proper morphism between two algebraic varieties, then you can actually construct a push forward from the group of constructible functions on X to the group of constructible functions on Y in the following way. So, okay, I have to, in order to tell you what is the image of something here, it's enough to just tell you what is the image of some indicator function 1z. So maybe I'm going to write it here on top since I have lots of space. So yeah, so let's just see what is the push forward of 1z. Okay, so this has to be some constructible function on Y. So I have to tell you what is the value of that constructible function on some element of Y. So this is going to be the topological characteristic with compact support of the pre-image of Y intersected to Z. So there is, so we have this definition, and then there is the following theorem. The theorem actually has a long history. It was initially a conjecture by Deligne and Grothendieck. It was proved by McPherson in 1974. And the theorem says the following things. So, so X is as before. So X algebraic variety. So it could be singular. Then there exists a unique transformation. So there is a unique C star, which goes from constructible functions to homology. You can upgrade this to Chow and so on, such that two properties hold. First of all, C star is functorial. C star is functorial. So functoriality just means what you think it should mean, which is, if you have a proper morphism between x and y, then you have push forwards at the level of both constructible functions and at the level of homology. So this is the transformation here. And here you have the push forwards in both situations. And then you want this diagram to commute. And the second condition, it's a normalization condition. A normalization condition that says that if x is smooth, then the image of the indicator function of x, it's the total Chern class of the tangent bundle of x, but you have to regard it in homology. Total Chern class is a cohomological quantity, so you have to cap with the fundamental class of x. Okay, so in particular, if you take, so as an example here, sorry, Mark, if you take the map, so if x, let's say that x is proper, so I have a proper map from x to a point, then the push forward, which is just the same thing as the integral, so the push forward of this class of the image of C star of 1x is, by the definition of the push forward in constructible functions, it's exactly the topological characteristic. Okay, so I'm going to drop the compact support after a while. Okay. So this class, let me make a definition. So in general, if you have Z inside X, constructible, then the CSM class, so the Chern-Schwarz-McPherson class of Z, is by definition the image of this McPherson transformation of the indicator function of Z. So this is called the Chern-Schwarz-McPherson class. So you may ask at this moment, oh, so we have Chern, which is because these are Chern classes. You have McPherson, because McPherson proved the theorem. So what is Schwarz? So Schwarz is Milen Schwarz. It turns out that this transformation that was defined, well, it was not, yeah. So it was defined and proved by McPherson to satisfy these properties in '74. It turns out that the same class up to a certain duality, the Alexandrov duality, was actually defined maybe a couple of years earlier by Milen Schwarz. But people did not realize, because of this duality was non-trivial, people did not realize that the transformations were the same. And in fact, it was realized much later. I think it's like beginning '80s, where McPherson and Milen Schwarz actually checked that the class of that was defined by Milen Schwarz actually satisfied the same properties as the one defined by McPherson, and therefore the classes must be the same. And in fact, the difficulty in this theorem, it's not the uniqueness. So I'm saying, okay, there exists a unique, but uniqueness is kind of clear here. For example, if you think about resolution of singularities, everything can be reduced to the smooth case where the normalization is going to tell you what to do. The point here is the existence. You actually have to construct such a class in such a way that these properties do hold. And yeah, so let me give you maybe a couple of examples to kind of like get your bearings about like how these classes look like in some simple examples. Right, so the CSM class of a point, well, what can it be? The point is smooth. So the CSM class of a point is a point. How about the CSM class of, let's say, A1 into P1, right? So I want to regard things inside some ambient space, which it's good to specify. At some moment, I'm gonna forget to specify it, and then it's gonna be understood from the context. But right now, we do specify it. Okay, so here we use additivity. So this is gonna be the CSM class of P1. inside P1. So P1 is just A1 union a point, right? So this is the class of P1 minus the CSM class of the point. That's because the indicator function of A1 is the indicator function of P1 minus the indicator function of that extra point. Now P1 is smooth, so you can just calculate. You can use the normalization property to get this. Of course, you must get 2 here because that's going to be the other characteristic of P1. So minus a point, right? So what you get here, it's the class of P1 plus the class of. Notice also there are 2 ones here. There is 1 and then there is the second one, but they kind of play different roles. So the first one is telling you that I'm really taking this P1 as the closure of A1 inside the ambient variety, and that class comes with multiplicity 1. The second one is telling you that the topological Euler characteristic of that A1 is equal to 1. So they kind of play different roles. They tell you different things. Okay. The second line, this one. Yeah, so this is because 1 P1 is equal to 1 A1 plus 1 over point. So therefore, I was writing the CSM class of A1, which by definition is just the C star of 1 A1. And I was writing it as the C star of 1 P1 minus the C star of 1 of points. And then I just calculated both. Oh,
where does the 2 come from?
Oh, this one. Yeah. Oh, yeah. This is the total Chern class of P1. P1 has all the characteristic equal to 2. So I knew to start with that this 2 was there, just because the topological characteristic of P1 is equal to 2. So essentially, the part of degree 0 of this class, it's always a point times its topological Euler characteristic. You can go a little bit further. You can get things like, for example, yeah. So let's say that you have something like this. So maybe you have some x0 in X with the property that this is open and dense. And let's say that the boundary of this x0 it's a simple normal crossing divisor. Then a very nice theorem of Aluffi says that the following is true in this case. It says that the CSM class of x0 is just the total Chern class of differential forms with logarithmic poles for this divisor D. Oops, you have to take the duals. And you have to homologize everything. So in particular, in some nice situations, you'll understand this very well. For example, in the toric varieties, and if x0 is the big torus orbit, this is trivial. So in that situation, this tells you, so if x is toric, and x0 is the torus orbit, so the T orbit, the big T orbit, then according to this formula, because this differential force with logarithmic poles are trivial, it's a trivial bundle, and the CSM class of x0 is just the fundamental class of x. It's very easy. Okay. All right. Okay. Good. So I mean, yeah. So the class this is naturally leaves as a homology class. It's naturally a homology class. Now, if X is smooth, of course it doesn't matter, right? Because you can take Poincare duality. You can also upgrade this to Chow, and then it really doesn't matter, because if you have Chow for smooth, it's the same. The homology and cohomology of Chow are the same. So yeah, so naturally this leaves us a homology theory, but in the presence of smoothness, which is actually very convenient. So what is important here is that you're trying to calculate the class of some z in some ambient space. So maybe you want your ambient space to be smooth, and then you can. Okay. So right. So what are the mother classes? Well, the mother classes are actually show up in the way Macpherson defined this transformation. So I'm kind of like reversing the history here. So let me just tell you a little bit about the mother classes. I'm going to give you a definition that I don't quite understand, and then I'm going to give you a definition that I understand slightly better. Okay, so right, so Macpherson actually defined a particular constructible function, which he called local Euler abstraction. So this is some constructible function, EU z. So the story is that z, this is the setup. So you have some z in X. In this case, you want to be closed. So z, you want z closed in X. So EU of z is going to be some constructible function in there. And then this constructible function has some properties. They don't determine the function, but you know, just to get an idea of what this is. So if z is smooth, then this local Euler abstraction, this EU of z, is just it's just the indicator function of z. And also, if you have some type of Whitney stratification, so let's say that you have a Whitney stratification with some strata here, then what you have here is you can write. So first of all, the local Euler abstraction is going to be constant on the strata, and you can write this function as a sum with some multiplicities times that. So I'm not exactly telling you what these multiplicities are, and this is where the difficulty is. So in particular, this will tell you that, well, so I didn't quite tell you what this is, but hold on. If once everything is defined, and I imagine that the people on the other side of the room can't see anymore, but okay. So once everything is defined, the mother class is just the image of Macpherson transformation of this local Euler abstraction. And in fact, Macpherson defined this first and used it to actually define that transformation over there. So let me give you a second way to do it, which is in some sense more explicit, and in some other sense, it's also very difficult. So this was happening, as I said, 74, right? So mid-70s. Many things happened in the 80s, and among other things, Kazan-Lustig theory came up, and perhaps related to that, there was a second way to define everything here. It's called the Lagrangian model to define these functions. So the Lagrangian model, so I'm going to give here some statements that I attribute to Ginzburg and to Claude Sabat independently in 1986. The precise statement I'm giving you is really, it can be found in Sabat's, one of Sabat's papers. So, okay, it says the following. So let's say that we have z in X, and now let's consider X to be smooth. So we want to look at the cotangent bundle of X. And this cotangent bundle sits over X, and it has a zero section. This is the zero section here. Okay. Let's also say Z is irreducible. Okay, so then I can look at the conormal space. The conormal space of Z in X. Now you may complain and say, well, what if Z is singular? What is the definition of this? This is by definition a Zariski closure. It's the Zariski closure of the regular part inside the cotangent bundle, inside the total space. So of course we know that Zariski closures are bad operations in algebraic geometry. So this is a difficult thing to understand, but it will be, if Z is irreducible, this is going to be also irreducible. And in fact, it's a theorem by Kashiwara, also proved independently Kennedy, that these are the only conic Lagrangian cycles inside the cotangent bundle which are irreducible. Okay, so what is the statement? The statement is that the mother class, oh, right, one more thing. So this is a bundle here. So it has an extra action over C star, which I'm gonna put, so with C star and the character minus H, where the H bar is the Planck constant. So this is not quite the language that Sabah and Ginsburg were using, it's more modern language, but it fits very well here. So this is essentially a restatement of what Sabah is saying. So the mother class of Z, and then I'm gonna have to homogenize it. It's equal to the pullback via the zero section of this conormal space, regarded as a fundamental class in C star equivariant cohomology of the cotangent bundle. Okay, so everything is now with respect to this C star action, and this is gonna be a class in H0 C star of X. Just because this is gonna be a Lagrangian class, so the codimension of this class inside the cotangent bundle is equal to the dimension of X itself. You're pulling back via the zero section, so you get something in degree 0, but you get something in degree 0 which is C star equivariant. Now think this C star doesn't act on the base, it doesn't act on the zero section, it only acts on the fibers, it rescales something on the fiber. So the base is actually fixed under the C star, and because the base is fixed under the C star, this is the same thing as essentially just H star of X, and then you homogenize. So maybe I should say this is included in there. Okay, so essentially, if you want to think of what does it mean that you are a class in the C star equivariant homology in degree 0, well, it's the same thing as giving me a non-homogeneous class in X, which you homogenize with the character H. For example, if I have a class in degree 2, homological degree 2, I'm gonna add an H squared to it so that it lives at the end in degree 0. Okay, so homogenization, dehomogenization, it's a property, and yeah, so this is the statement. So here you have to homogenize the mother class. The mother class will be a non-homogeneous class. You homogenize it so that it lives in the 0 part, so that this makes sense. So this is the definition of the mother class from this point of view. So in some sense, the mother classes really correspond to this conormal cycles. And in fact, this Lagrangian perspective is much rich. So this is a diagram that appeared in one of Ginsburg papers. Again, so this is Sabah 86, and maybe this is Ginsburg 86. So it goes like this. So here I have something in the middle. Okay. So what is this? These are called the conic Lagrangian cycles. These are conic Lagrangian cycles in P star of X. So this is a formal combination of, essentially it's a formal combination of things like this with some multiplicities. That is a conic Lagrangian cycle. So this is inside T star X. What you can do is you can apply the pullback via the 0 section to that. There is a map here called the characteristic cycle map. This characteristic cycle map is uniquely determined by the condition that there are always signs in this story. So if you take -1 to the dimension times the Euler obstruction, then you get the conormal space. And this characteristic cycle map is actually an isomorphism. So in some sense, not in some sense, in a precise sense, this identifies this with that. And okay, so the mother classes really correspond to these conormal cycles. And now what you have some interesting examples of conic Lagrangian cycles that come from Kazan-Lustig theory. And because of this map, you will also have the corresponding constructible functions associated to them. And you can have a little diagram. So the diagram is going to be like this. So let's say now that X is a G mod B. So I think in this audience, I don't have to say what G mod B is. Complex semi-simple Lie group, and B is a Borel subgroup. And then this X has a stratification by Schubert cells. My conventions are in such a way that the dimension of the Schubert cell is equal to the length of the Val group element. And then you can do the following, you can construct the following diagram. So you have on one side, you have the CSM class of the Schubert cell, which, recall, this is just C star of the indicator function of the Schubert cell. A Schubert cell, it's a constructible subset. On the other side, you have the mother class of the Schubert variety. So mother classes are associated to closed subvarieties. So this is the same thing as the C star of this Euler obstruction. Yeah, for this XW. Okay, and then there is a. You can go from one to the other using some coefficients here. The coefficients are called the local Euler obstructions. So XW. I'm going to put here just W and V. But really, this is the value of the local Euler obstruction for the Schubert variety W at the fixed point V. So this is an integer, in fact. It's a very mysterious integer, and I will try to convince you that we don't know it, even now. Okay, on the other side, there is another class, which is called the Kazan-Lustig class of the Schubert variety. So this Kazan-Lustig class is the class which is associated to a particular constructible function coming from the intersection cohomology complex of the Schubert variety. How do you do it? Well, okay, I'm just going to brush through the details, but essentially what you do is you take the intersection cohomology complex, and then you take the associated perverse sheaf, and then you take the stockwise Euler characteristic, and then that will give you a constructible function. So this is chi-stock of IC of XW. Okay, so we have these three things, these three classes. They all live. All these are classes. So all these everything happens here in the homology or cohomology, doesn't matter, of G mod B. What do we know about this? So as I said, the transition matrix between the mother class and the CSM class is given by this mysterious local Euler obstructions. How about this transition matrix? Well, this is exact V. This is going to be, so I have a Schubert variety, and the Schubert variety is paved by Schubert cells, and I'm going to look at the fixed point corresponding to V, the little v, in the Schubert variety XW. In particular, V is less or equal than W in the Brucha order. It's a fixed point inside it's a torus fixed point inside the Schubert variety. Okay, so the Kazan-Lustig theory comes here. The matrix that relates these two classes is given by the Kazan-Lustig polynomials evaluated at 1. If you want to see the full Kazan-Lustig polynomial, I'm going to have to upgrade this to K theory, but this is a talk about cohomology. So this is when Q is equal to 1. Okay, so you can see that we have this thing here. Maybe let me say one more thing. So, right. So if you look at the characteristic cycle of the IC sheaf of a Schubert variety, so this is going to be some element inside these conic Lagrangian cycles. It has some irreducible components, but we know what the irreducible varieties are. So they are just conormal spaces associated to the Schubert varieties. So there must be some multiplicities here. So this multiplicity is MWV. So this diagram here, so everything talks to each other, right? So the CSM class and the Kazan-Lustig class talk via the Kazan-Lustig theory. The CSM class and the mother class talk through this local Euler abstraction. The mother class and the Kazan-Lustig class talk to these multiplicities of the decomposition into irreducible components of the characteristic cycle. In particular, a very interesting problem that was posed by Lustig was when this characteristic cycle is irreducible. It was actually expected to be irreducible, for example, in type A for all partial flag varieties, until Kashiwara and Saito found out the counterexample in type A7, so for FL8. So, so irreducibility is going to be detected by this type of thing. So I'm just going to say this. So remark, the characteristic cycle of the IC sheaf of XW is irreducible if and only if the Kazan-Lustig class of XW is equal to the mother class of W. So this is a slightly different perspective on these mother classes. They tell you that essentially because they play the role of these conormal cycles, and the conormal cycles are the irreducibles in the cotangent bundle, every time when you're able to expand things into the mother class, you're going to be doing some type of operation, some decomposition inside the conic Lagrangian cycles. So yeah, so this is so then the question is, well, do we know anything about this irreducibility? We know very little about the irreducibility, and essentially the only facts that we know about irreducibility are coming for these Cominuscule Grassmannians. So for example, if you don't work in the full flag variety in the G mod B, but if you work in these Cominuscule Grassmannians, then for the Cominuscule Grassmannians of simply laced types, this is known to be irreducible. And I'm gonna explain to you how we can calculate the mother class in that situation, and we'll be able to see explicitly maybe some calculations. Maybe explicitly, maybe not in the talk, but if you look in the paper, definitely, so you will see some explicit calculations. Okay, so right, one more thing, maybe which I should point out here. So I'm making some statements about, well, it's very interesting to understand this arrow here, but okay, well, this arrow, any of the arrows here is determined by the other two arrows, right? So in particular, this arrow we know the Kazan-Lustig. So there are algorithms to calculate Kazan-Lustig polynomials. In particular, there are algorithms to evaluate them at 1. But the question is, can we actually calculate CSM classes? And the answer is yes, we can calculate CSM classes. The calculations of CSM classes is well developed. I don't want to say too much about it. I'll just say that calculations of CSM classes of Schubert cells are encoded in the, so calculations of CSM classes of Schubert cells are given by the Hecke algebra action. It's a particular degenerate Hecke algebra action in this case, are given by the Hecke algebra. Algebra action. So let me just I'll just say something which is extremely vague, but I'll just say the following. So okay, so we have the homology or cohomology of G mod B. By the way, bifunctoriality, once you do it for G mod B, for CSM classes, bifunctoriality, you also have it for any G mod B's. You can push forward via some proper morphisms. Okay, so we have a Hecke algebra action here. That Hecke algebra action has some has the standard basis, which is given by some elements, TW. So these TWs act here. So normally I should tell you how the TIs, so the ones corresponding to the simple reflections, act. And there is a very nice formula for that. It's given in terms of certain de Mazur operators and the right Weyl group action here. But I'm not going to write it. I'll just say the following, that so this is a theorem that was developed, well, we proved it with Paolo, but then there are several other versions of this. So it says that the CSM class, so this is a theorem, CSM class of the Schubert cell is the image of the operator of the standard basis operator for W inverse acting on the class of a point in the homology of G mod B. So what Hecke algebra am I considering here? I'm considering a particular degenerate Hecke algebra. Is the Hecke algebra which satisfies these relations. Ti squared is equal to 1, and Ti plus 1, Ti is equal to Ti plus 1, Ti plus 1. This is the type A story, but there is an analogous of this for all types. So this may look a bit suspicious because they look like the relations in the Val group. But this is a twisted action, in fact. It's not the one. So there is a twisted action which was defined by Leclerc, Lascaux, and Thibon. And that's the action. One can write down the operators. If you're interested, I can tell you more about it after the talk. So there is a twisted action, and you get something called the degenerate Hecke algebra that was also considered by Ginzburg. And then if you use those operators, and if you act on the class of a point, then you get these CSM classes. This is, I mean, for computational, from the computational point of view, this is explicit. So the computer will know how to deal with this in any medium-sized cases. So in some sense, this top part of the diagram, in some sense, is known. This part is also known because we know the Kazan-Lustig. It's this part that is missing. So if you figure out any of these two things, you're going to figure out the other one. Okay. So, right. So how do we calculate? How much time do I have? 15 minutes? Okay. 12? Okay, I have, okay. It's the clock. Okay, so, right. So I want to tell you how you calculate mother classes and where Rahul comes. So we wouldn't have been able to do that without Rahul's observation that you can actually desingularize normal spaces of certain Schubert varieties. So these are the two facts that are needed. And these facts are not super hard to prove. So calculate mother classes. So what do we need to understand? If you remember the previous board, I guess, these are related to the conormal spaces of the Schubert varieties. So what are the two things that we need? So the first fact, it's a theorem which it resembles very much with what Fulton does in his intersection theory book. It says the following. So let's say that you have some cone. In other words, it's going to be stable under the C star action here, inside the cotangent bundle. Then if you pull back this cone via the zero section, and if you homogenize everything, so everything needs to be taken with respect in a C star equivariant way with respect to some character chi. This is the same thing as taking this intersection theory operation. You take the total Chern class of the cotangent bundle and you intersect that with the Segre class of the cone, and then you homogenize everything with respect to the character chi. So this is going to be some class which lives in this C star equivariant homology. So what is this Segre class? So this Segre class, it's an operation which is very useful in intersection theory. It's defined essentially in the following way. So I'm redrawing the diagram. So you have this T star of X, you have X here, and this T star of X actually has an open embedding in its projective completion. And then you have a projection here which is proper. And the Segre class of C of this cone is just a push forward of the closure of the cone inside here, divided by well, it's going to be a C of, so it's 1 plus C1 of, let me put 1 minus C1 of O of 1. So O of 1 is the dual of O of minus 1, which is on that projectivized bundle. So Segre classes know about this pullback via the zero section. This is essentially, if you follow closely what Fulton writes in chapter 3, you're gonna end up here. Okay. And then the second thing is that you still need to calculate Segre classes. And so the second fact is that Segre classes behave very nicely under birational push forward. So if you have something like this, I'm a bit imprecise here, but I'm going to write it. So if you have some conormal space which sits over some z in some x, and then if you have, let's say you have a cone here, and these maps are birational, and then this lives in some x prime. This is a fiber product. This cone lives over C prime. So this is a cone. This is a cone which lives in the pullback. So everything here is with respect to the cotangent bundle. So you pull back the cotangent bundle from x to x prime, and then this cone is supposed to live inside that pullback. Then the pullback of the Segre class is this thing, is what we want. So the strategy here is to, one more thing about Segre classes, that in some situations, you can actually say what they are. So for example, if the cone happens to be the class of a vector bundle, the total vector bundle, total space of a vector bundle, then the Segre class is 1 over the total Chern class of that vector bundle. So that's the idea here. The idea is to desingularize, to find the resolution of singularities of such a conormal space by the class of a vector bundle. Being a class of a vector bundle, you will know what its Segre class is, and then you'll apply this formula. This is what Rahul did. Rahul exactly found a desingularization of these conormal spaces in the cases when the flag variety is a Cominuscule space. So I will not define Cominuscule spaces. I'll just say that this is a family that includes the Grassmannian in type A. So let's say that X is G mod P is a Cominuscule space. And so, as I said, these are Grassmannians in type A, Lagrangian Grassmannian in type C. We have the maximal orthogonal Grassmannian in type D. We have the quadrics, both even and odd, and we have the Cayley plane in type E6, and it depends on your convention. It's E7 over P7 is the long branch. So the Freudenthal variety in type E7. So it's a small list of homogeneous spaces. And now what is nice about this is that their Schubert varieties are indexed by combinatorial objects, which essentially look very much like partitions. And I'm going to explain this desingularization in the case of Grassmannians. This is Rahul's result. So, okay, so let's take a Schubert variety. Let's take a Schubert variety indexed by some partition in some Grassmannian. And for simplicity, I'm going to just draw. I'm going to take one particular Grassmannian. Maybe, let's see how big this is going to be. Okay, I'll do it this way. This is going to be GR37. GR37. Let's pick a partition inside this GR37, inside this box. Maybe we have this partition. So the partition here is going to be 3, 2, 2. Okay. You can read a lot of combinatorics out of this picture. For example, you can read the inversion set of the Val group element which corresponds to lambda. And this is how you read it. So we are in GR37. We have the simple root here, which I'm going to write E3 minus E4. And I don't want to write E, so just 3 minus 4. Then 3 minus 5, 3 minus 6, 3 minus 7, 2 minus 4, 2 minus 5, 2 minus 6, 2 minus 7, and so on. Okay. So So for this lambda, there is a W lambda associated to it, right? There is a minimal length representative which corresponds to this partition. And then the inversion set, so the I lambda, which is the inversion set, so those positive roots, which are not in the parabolic P, with a property that V lambda of alpha is less than 0, can be read from the roots that you see inside the diagram. So in this case, there are going to be all these 3 minus 1. We have 1, 2, 3, 4, 5, 6, 7, which they should be because they give you the dimension of the Schubert variety. Very good. So what is now Rahul's observation? So what I want to do is I want to take this particular Schubert variety, which is drawn there, and I want to look at the conormal space. The conormal space at a particular point, namely the smooth point in the middle of the Schubert cell corresponding to lambda. So that one will correspond essentially to this part here. So these roots, the roots which are outside lambda. So technically what you're writing, it's W lambda inverse of, so this is the conormal space of X lambda at the point E lambda and inside G mod P. And then this is going to be, so you want to kind of translate everything at the origin. So this is going to be just the sum of some roots, positive roots, which are not in the inversion set. So the observation is that this, in fact, is a B module under the joint action. And this is where the Cominuscule hypothesis is used. Why is it a B module? Well, you want to act on a root here with some other root. Could be simple, could be non-simple. The point is that all the roots here have this root, E3 minus E4, with multiplicity 1 in them. So if I'm going to add any other root to this, I can never go back. Either I go outside the box, in which case the action is trivial, or I stay inside this side. So why is this useful? Well, this is useful because once this is a B module, we know from geometry, you can construct bundles using homogeneous bundles using these B modules. So we can construct in this case something like this. So it's this space here, right? Which leaves over G mod B. But I want to restrict it, in fact, so this is going to be restricted. Yeah, let me just say it is over G mod B. Okay. So I will restrict now, so that everything leaves over the Schubert variety in G mod B, which maps birationally to this Schubert variety in the Grassmannian. And then that one has the conormal space associated. And then there is a natural map here. So there is a natural map because this was a B module. And this map is birational. Because it's going to be an isomorphism over the cell. Over the cell, everything is smooth, so everything is fine. So then we are exactly in the situation of this. So we are there, and therefore we can write down what the theorem is. And is it visible if I write here from the other side of the? Let me just tell you what the calculation is, and then I'll give two corollaries short. So this is the theorem. As I said, this is myself and Rahul. It says the following: that if you take a Schubert variety inside one of these G mod P's, which is Cominuscule, then the mother class of the Schubert variety is just the push forward. So this is going to be just the projection here, right? This is inside G mod P, inside G mod P. So there is a projection. So is the projection. So you still have to do something. This is the conormal space. You have to still deal with the first part of those two facts. So what you will get in the end is going to be the product. It's going to be 1 plus the first chain class of the homogeneous bundle. So my time is up. Okay. I'll hit clear. which I don't. So can I take maybe 3 minutes? Okay, thank you. Okay, so right, so we have minus alphas here. So these are the homogeneous line bundles on G mod B, and they have first chain classes. And you take their total chain classes, you take the product of all of them. So this is going to be all the alphas in R plus minus RP plus with a property that W alpha actually is less than 0. So this less than 0 has to do with the first part of that. And that is the mother class. So is the intersected to, right, one more thing. Everything intersected with the fundamental class of the Schubert variety inside G mod B. So this is the formula. Now, it may not look very impressive or anything, but for me, this is just the Chevalier formula. So if you work in Schubert calculus, you know how to deal with this multiplication. At least the computer will know. So in particular, we can write down explicit examples in all the Lie types uniformly. This is the uniform formula across all Lie types. And then one of the corollaries is that, well, it was already known by work of Bressler, Finkelberg, and Lunz in type A, and Bow and Fu in types A to D, so in classical types, that the characteristic cycle of the IC sheaf was irreducible. So that means that the Euler obstruction is equal to the Kazan-Lustig multiplicity in that situation. But how about types E6 and E7? So in that situation, it was not known. Well, using this formula, you can, it's a bit unsatisfying, but we had a brute force Sage algorithm. We just checked that the mother class was equal to the Kazan-Lustig class in those situations, and you obtain the following corollary that says that, let's say that G is simply laced, and G mod P is a cominuscule, so in other words, is the minuscule one. Then two things happen. The Euler obstructions, E, U, W, V, are equal to the Kazan-Lustig polynomials evaluated at 1. And the second thing is that the characteristic cycle of the IC sheaf of XW is irreducible. So this is a different method from anyone else, but we could not check irreducibility directly for the classical types. But at least it gives you a calculation. The second corollary that I'm gonna just mention super fast is that, well, once you say that the local Euler obstructions are equal to the Kazan-Lustig polynomials, you know that the Kazan-Lustig polynomials are positive because you evaluate them at 1. So this implies, so this is a corollary 2. This implies that the mother class of the Schubert variety, in fact, it's an effective class if G mod P is minuscule. And it's not just effective, it's strongly effective in the sense that if you expand this class in terms of Schubert varieties, each Schubert subvariety that should appear here does appear with a positive multiplicity. And in the cominuscule cases, you only get this. That's because we cannot prove it, but we believe, so in general, this is true for G mod P cominuscule. But we conjecture is actually with strictly larger. And then if you're curious, you should look in the paper. We have also log concavity conjectures and other things that we don't quite understand where they are coming from. So I'll stop here. Thank you very much.